Now, when we're talking about this in terms of hypotheses, then we need to put on our little hypotheses hat, and we're back in the realm of directional and non-directional. In non-directional, we're using that language to say that it is simply, there's a difference. These things are going to be correlated, but we're not putting any pretenses out there in terms of how are they correlated. Positively, negatively, weakly, strongly. We're just simply saying they are not, or they are. And if they're not, that is the null. The null always assumes that there's no relationship, no differences here. And so the symbol form is going to say that your r is equal to 0, because if r is 0, there's no correlation. Whereas if r is not equal to 0, any number other than 0, then there is some correlation. That correlation could be positive, it could be negative, it could be strong, medium, weak, any type. It's just some correlation. We'll change our gears a little bit when we're in directional hypothesis testing, because now we're saying that if we believe that the correlation will be positive or it will be negative as it compares to not correlated. So the null is still saying r is equal to 0, but we have one possible alternative where we say that r is greater than 0, and if it's greater than 0, we infer that there's a positive relationship, positive correlation. And if r is less than 0, then we're saying that they are negatively correlated. They have a negative relationship and association. Now, you don't really say both alternatives, that one is greater than and less than 0 at the same time. You're only going to state the one that you believe that you're going to find. Otherwise, you'd just be using the non-directional version. So let's talk now what happens about something called the coefficient of determination. Ooh, that sounds like fancy stat stuff, but it's a really simple concept. And in this case, it's r squared. The coefficient of determination, or r squared, is just the squared value of r, not too tough, but it has a special definition and a special place for us. We've already started talking about r squared in previous videos, most notably and recently in our one-way ANOVAs, when r squared was equal to eta squared and was an effect size for the one-way ANOVA. And here, it has the exact same definition, calculated a little differently, but it has the same definition where we're talking about the variation in one variable that can be explained by the other variable. So all we have to do is treat it as another effect size. Now, I'd like you in your notes to keep a track between r and r squared. R squareds, when you square r, it's going to become a smaller number when it's a decimal form. That's just how the math works. So we're going to tamper down our french fry size scale for the r squareds. Keep in mind r has an effect of plus or minus 1, plus or minus 0.1, plus or minus 0.3, plus or minus 0.5 for small, medium, and large respectively. And r squared, we're going to go real low, and we're going to do plus 0.1, plus 0.01, plus 0.09, plus 0.25 for small, medium, and large respectively. Note that all of the r squareds are positive numbers because when you square r, even if it's negative, you're going to get a positive number. And that what we're saying is this is the proportion or percentage, if we converted it, the amount of variation that can be explained. Even explaining 2% or 5% can still be a meaningful contribution when you're talking about why another variable varies. There's a lot of reasons in the universe as to why something is what it is. So even explaining small amounts can be substantive, at least in the social sciences. So I just wanted to show you these two plots. We saw them before, but I have them back up here where we have the association, positive correlation and negative correlation for appreciation for rock at different ages. And in the one on the left, we have r is equal to 0.6. It's a moderately strong correlation value and positive in nature. When we square it, we get 0.36, which would say that 36% of the variation in appreciation for rock and roll could be understood by knowing someone's age. Contrast that with the one on the right, where we have a strong negative correlation at negative 0.8, and it squares to 0.64, which we could say 64% of the variation in appreciation for rock and roll could be understood by knowing someone's age. So pretty simple concept when we just kind of take it down to its nuts and bolts. Let's talk briefly about causality. Causality is a real important thing when we're talking about statistics here, and I cannot stress hard enough that correlation and causation are not the same thing. They're just not. Please Do not say and confuse these things. Now, you can have very strong correlations. You can have incredibly perfect strong correlations. It does not mean that one variable, because it's perfectly correlated with another, is evidence and proof to say they're causally related. Why these things have an impact and change in the real world. The classic example we can use with this is ice cream sales being correlated with crime. Now we can get real world data, and people have done this on many occasions, and show that when ice cream sales go up, so does crime. But is ice cream sales really causing more crime? Or conversely, if there's more crime going on in the neighborhood, does this mean that we're getting more ice cream sales? No. It has what we call a third variable problem. Third variables can also be called confounding variables, lurking variables, omitted variables. They go by different names depending which disciplinary circles you're working in. But they keep the same idea, that the relationship that you're finding between two variables can actually be explained by another one that's not being taken into consideration here. And in this case, the causality issue that we're finding is being taken up by a third variable. If we're talking about ice cream and crime, they're both going up, but so does temperature. Temperature is a third variable. When the temperature goes up, it gets warmer out, people want more ice cream, and they go buy more ice cream. So as temperature goes up, it's highly correlated with ice cream sales, and it's causally related. Also, as temperature goes up, crime happens to go up. People tend to be out more, and it just so happens to be, by people being people, that more crimes are being committed at this case, when they'd rather be doing it in summer than in the dead of freezing cold winter, or so it seems for the most part. So they're not just correlated, but they're causally related as well. And the direction of causality is just something that we have to come up with by knowing the real world and how variables react to each other. The correlation coefficient you get itself, that R value, says nothing about the way that these variables are causing each others to change. That has to come from real world knowledge. And so with that, it's going to go ahead and wrap up our video section here on the introductory topics for correlations. I'll see you all in the next video, where we're going to calculate covariance and the correlation coefficient R by hand and do our first significance test with it. I'll see you then.